Alright, so today we are discussing curvature. What is curvature? It is actually the, you can say that if whenever we have a curve, it bends, right? Let's see something like that. So if I want to measure how much this curve is bending, right? How much there is a turn in this curve. For example, if I have a straight line, there is no bend in it, right? So the curvature will be zero here. Okay, because it's not curved, so curvature is zero. It is not curved, so no curvature, right? So curvature comes from the curving of the curve, well, how much it has this curve. So if there is a small bending like that, curvature will be small here, right? Here there is more bending, right? So curvature will be big here. So that's what we mean by curvature. So the notation that we use for curvature is this k, but this type of k. It's not k actually. It is kappa. Uh, K A double P A. This is the notation for the kappa. It's similar to k. It's again a Latin letter like alpha, beta, gamma, right? Alpha, beta, gamma, delta, etc. So there is one kappa here. So it's not just k. We make this line like s, right, and then make it a k. So this k is kappa notation for curvature. Notation for curvature. And simply, if you have a function y is equal to f of x, right, is a given curve, at every point I can define curvature, because at different points the curvature will be different. For example, if my curve is like this, right, let's say curve is like this, then what do you think? Curvature at this point will be very small, right? At this point little bigger, because the bend is little higher, and here there is highest curvature will be here, right, because there is more bend. Again, if it gets, let's say, straight, then curvature will become zero. So at different points I can get different temperature. At this point different, at this point different, at this point different. So at every point I can find the curvature. So the formula for the curvature is that you have to find the second derivative, d2y by dx square. If it is negative, make it positive, and divided by 1 plus dy by dx square root. Not square root, it is power 3 by 2. It is power 3 by 2. This, if you look at the derivation of this formula, it comes from the arc length. Remember the arc length parameterization. Arc length was 1 plus dy by dx square and square root. This was the formula for the arc length in section, I think, 6.4. Right? So they use this arc length parameterization for this curve and obtain the formula for this bending from there. That's why you see this type of term is coming, 1 plus dy by dx square in the middle. But we don't need to go to the derivation of the formula. We can just take this formula as it is and implement that, right? So you can also write this as, you know, that the second derivative can also be written as f double prime of x. So we will take the absolute value here, and 1 plus f prime x square power 3 by 2. So whatever formula is easy for you, you can use it. Either write dy by dx or f prime, d2y by dx square or f double prime. Both are the same, right? Similarly, at each point, you can also draw. Should we go? Sometimes it's just, they just do it, just check it. And now you see here at each curve, if the curvature is changing, right? Curvature is changing. You can also define a circle which is a circle whose, you see, at this point, if I follow this bend, if I follow this bend and complete a circle here, right? If I follow this bend and complete a circle, it will be little bigger, right? You see here, agree? So at each point, I can draw a circle depending on this bend, right? And the radius of this circle comes from the curvature basically. We call it the rho. Here the radius is smaller, right? Radius is bigger. And so if I just keep on going, why this is not changing. So anyway, this rho is called, rho here is called radius of curvature. Radius of curvature, because it is related to the curvature. If there is a more bend, then the radius will be smaller. If curvature is bigger, radius is smaller. You see, if the bend is big, then you see I will make a very small circle here, right? Based on this curve. If the bend is small like that, and if I follow this bend, right, the circle will be very big. Agree? So it means the kappa, curvature small, right, gives rho big, right? And if kappa is big, like here, if the curvature is big, then circle will become very small, so radius will be small. So your radius of curvature is given by 1 over kappa. You just take the reciprocal of curvature, gives you the radius of curvature. Okay, so if the curvature is big, 1 over k will be small, 1 over kappa will be small, so rho will be small. Again, this rho is not p, right? So this is not a p, it's rho, which is again a Latin letter, or ho, rho. Okay, it's again like alpha, beta, gamma, delta. So rho and kappa, they are both Latin letters. So if you can obtain a curvature kappa, you can obtain this rho by just dividing kappa by 1. So this will be the radius of curvature. So both things can be obtained. So let's say, as an example, if I take y is equal to some x square, simply, right, a simple and maybe the point is 1 1, let's say. So we know that x square is this, right? This is y is equal to x square, and at 1 1 I may have a very big curvature, because you see the bend is not that much, right? If I take 1 over if I take x cube, maybe the bend is more at 1 1. Anyway, we can try that. Let's see what I get. So what do I need? I need two derivatives, dy by dx, which is 2x, and d2y by dx square, which is 2, right? So I got two derivatives. X square becomes 2x and 2x becomes 2. So therefore your formula for the kappa was second derivative divided by 1 plus first derivative square, dy by dx square. I will write this formula, so you don't have to worry about this one. If any formula is difficult, I will write it in the exam. Difficult formulas, not the simple ones. So this one, so if I replace, now the second derivative is 2, and no need to take the absolute value, right, because it's already positive. So something is positive, no need to take absolute value, it's already positive. So 1 plus dy by dx is 2x square and power 3 by 2. So if you want to simplify, there is no simplification, I guess it will remain as it is. So at the end I can just replace the point. So at 1 1 my kappa will be 2 over 1 plus x is 1, so 1 plus 2 square power 3 by 2. Because x is 1, so this will become 2. So 2 square is 4, so 4 plus 1, 5. 5 to the power 3 by 2. So if you want, you can use calculator and write the values in decimals. Otherwise, you can leave it like that. 2 over 5 power 3 by 2. 2 divided by 5 power 3 by 2. 0.178 almost. 0.17888. So I can say 1789. 179 can also be written here if you stop at 3 decimal places. And if you want, so this is the curvature, right? So if you want also the radius of curvature, if you also want the radius of curvature, so the radius of curvature is rho, which is 1 over kappa. So that will be 5 to the power 3 by 2 over 2. Just the reciprocal, right? Upside down. Or you can again just divide this by 1. If I divide this 1789 by 1, what you will get? 1 divided by the answer, which is 0.178. 5.59, right? 5.589, so 5.59 I can write. So this will be the radius. So see, when your kappa is small, 0.17 is a small number, radius becomes little bigger, right? So always remember, small curvature gives you a big radius, big curvature gives you a small radius. So that's it. I think there was if you look at the book, they define curvature in a very difficult way, so I just don't want to do that. They did it using calculus 2, the vectors basically. You see this topic curvature, and if you look at the formula for the curvature in this section, it's little difficult formula for the curvature. So that's why I did not go through this one from chapter 12. You know, chapter 12 is in your calculus 2. So this is the formula for the curvature, but this is written in a different way. If I change this formula to y is equal to fx form, I will exactly get the same answer that I had here, which I wrote here, this formula. Okay, so we can just directly do it. So here I opened notes from the website. Find the curvature of y is equal to x4 at 1 1, and answer is also given. So maybe we can try this one. Finding curvature is not difficult at all. You can also do your sine, cosine, or logarithmic function, or anything can be done, because if the point is given, then it becomes easy. So here x4 is given, and again the point is 1 1. Right, so I need the first derivative. First, remember that I need two derivatives, 4x cube, and then the second derivative will become 4 into 3x square. So this will become 12x square. So now if you can do two things. Let's see if your curvature is written here, d2y by dx square. The formula, I'm writing it again, 1 plus. If I put the values at the end or at the beginning, let's say, if I want to say that I want this curvature at the point, whatever point you have given me, at point x0, y0, let's say, I want that, I can directly replace the second derivative at this point x0, y0, right? And I can calculate first derivative at x0, y0, and then replace the values. Both are fine. You see, in above example, what I did, I first put the derivatives, I first put these two values of the derivatives in the formula, and after that I replaced the point 1 1. So what did I do? I replaced the point here but this was constant, so nothing has changed, and I replace the point here, it becomes 2, right? So it means I can find these two values at the point and then replace it here. That will also give me the same answer, and it will simplify our formula a little bit, because then we don't have to put the x values there. So excuse me. So at 1 1, if I replace the values 1 1, I can calculate both the derivatives. Dy by dx will become 4 into 1 cube, which is 4, and d2y by dx square will become 12 into 1 square, which is 12. So instead of putting the values at the end, I can replace the values in the derivatives, and then I can obtain this curvature, which is the second derivative at 1 1, which is 12, 1 plus the first derivative at 1 1, which is 4, and power 3 by 2. So see, this becomes a little easier. Instead of putting 4x cube, 12x square here, and 4x cube here, and then putting the value, it's easy that you just replace the values before and then put those values in the formula. So now if I simplify, it is 4 square 16 plus 1 17 power 3 by 2. Okay. So they wrote 12 17 over 289. 12 square root of 17 over 289. 289 is 17 square, right? So this is 17 power 3 by 2. So I think you can write this as, I think they wrote it as 2 minus 1 by 2. So if you bring 1 square root at the top, then in the bottom it becomes 17 square. You see, 2 minus 1 by 2 is 3 by 2. So if I write them together, 2 minus 1 by 2 is 3 by 2. So it means this is okay. This answer is fine. It is the same answer that is written in the book. 12 square root of 17 and 17 square is 289. So because they use a different formula, so maybe by using that formula they got this answer, but it is exactly the same which I got here. So you can either stop here, or power 3 by 2 can also be written as 17 into square root of 17. Anything power 3 by 2 is x square root of x, because 3 by 2 is 1 plus 1 by 2. 3 by 2 is 1 plus 1 by 2. So I can write x to the power 1 separately and x to the power half separately. So sometimes they write 3 by 2 as x square root of x, and that's how I can write. If you again use the calculator and want to write the answer in the fractions, in decimals, you can write that. So 17 divided by 17 into square root of 17. 0.242. 0.2425. That's your answer. And if you want radius of curvature, it is 1 over kappa, which is 1 over 0.2425, or 17 square root of 7 divided by 12. 1 over 245, it will become 1 divided by 0.2425. So 4.1237. Okay, so this is a very simple, easy topic. If this formula is given, you can easily find the curvature and the radius of curvature. If you want to try some other, let's say, sine cosine functions, you have a cosine function like that. So you see here your curvature will be the bigger at 0, at pi, you see, at pi or at 0. At pi by 2 it will be smaller. You see, it's almost a straight line at pi by 2. So k will be very small here. K will be small if you calculate at pi by 2, and if you calculate at pi or at 0, k will be big. because you see the most of the bend of the curve is higher at 0 and at pi. So if I try another example, I can write y is equal to cosine x and maybe take the value x is equal to pi at x equal to pi. So let's see what is the derivative. Dy by dx is minus sine x and d2y by dx square is plus cosine x, right? Sorry, minus cosine x. Now if I put the values, therefore at x is equal to pi, your derivative is minus sine pi, which is 0, and the second derivative is minus cosine pi, which is minus 1. So therefore kappa, the radius of curvature, is the absolute value of the second derivative divided by 1 plus dy by dx square power 3 by 2. So this will become absolute value of minus 1 divided by 1 plus 0 square power 3 by 2. So this has become 1. Minus 1 absolute value is 1. 1 plus 0 square is 1. 1 power 3 by 2 is also 1. So answer is 1. So see, the curvature is 1 here. And let's say if I want at x is equal to 0 as well, let's say not 0, pi by 2. Let's say at here where I am claiming that this curvature will be small here. So curvature becomes 1 at x equal to pi. So let's see what we have here at pi by 2. Should be smaller. So at x is equal to 0, dy by dx will become sorry, not 0, pi by 2. Minus sine pi by 2. Now sine pi by 2 is 1, and d2y by dx square, which becomes minus cosine pi by 2, and that is 0. So see, your curvature has become 0. So therefore the kappa is second derivative, which is 0, divided by 1 plus first derivative minus 1. This is minus 1. So minus 1 square. But doesn't matter what you have in the bottom. If the numerator is 0, everything is 0. So you see, what does it mean? If your curvature is 0, it means your curve has no curvature. It means it behaves like a straight line. Okay, no curvature. Only straight lines have no curvature. So it behaves like a straight line. Only straight lines have 0 curvature. So it means your graph at pi by 2 is almost a straight line. And you can see here, right? It's almost a straight line. It behaves like a straight line here. So almost, if I zoom it here, it almost behaves like a straight line, like a line. That's why your curvature has become 0 here. Your kappa is 0. So we already knew that your kappa has to be small here and big at pi. And see, the calculations also give you the same thing. If curvature is small, there is no radius of curvature. Sorry, not small, 0. If curvature is 0, radius of curvature is not defined, because radius of curvature is 1 over kappa. It's not x. Okay. So that is 1 over 0 is infinity. So we do not define radius of curvature here. Alright. So you can try some other examples, maybe. Try y is equal to sine x at x is equal to 0, x is equal to pi by 2. Let's say you can try this question. Another one you can try, because this topic is not in the book, so you can try y is equal to natural log of x, maybe, right, at x is equal to 1, and at x is equal to e. Maybe you can try that. anything else, square root of x. You can make many questions. Let's say in this exercise, if I have something, they may have given you the regular formula. Use the result in exercise 23b. So you see here, this one, they said if we have a simple 2D curve, if we have a simple 2D curve where x is given by where y is given as f of x, you see, this is what I'm doing, right? Then the curvature is given by d2y by dx squared. This is the formula we are using. Agree? So here in these questions, he said use that formula from 25 to 28. So maybe I can write uh, this portion over there. So you can try these questions as well. Right? So these are 6 questions. You can try that as well. So this is the same question which I wrote. Y is equal to sine x. This is 25th question. You see, 25th question is this which I wrote. Y is equal to sine x at x equal to pi by 2. So I also said at x equal to 0 as well. Tangent x at pi by 4. You see this 26 formula. Why they give you pi by 4? Because this is your tan x. At pi by 2 tangent becomes infinity. At minus pi by 2 tangent becomes infinity. So that's why they give you pi by 4 somewhere here. Find the curvature of the tangent x at pi by 4. So you can do that. And what you will do at 28? 27 is fine, but look at 28. So let me give you the solution for that. Why this 28 is different? Because in 28 y is equal to fx is not given. You can see that it is implicit, so you have to use 3.1. This is implicit function, so I need implicit function. Use section 3.1 in chapter 1 to find dy by dx. What was that? Implicit differentiation. So see, even though if your chapter 3 may not be included in your exam, right, because it was there in your midterm, I may need it. So we don't just throw everything away which is not included. So what is implicit differentiation? We take the derivative of each term, d by dx of y square minus 4 d by dx of x square is equal to d by dx of 9. So this is implicit differentiation, that we differentiate every term with respect to x. And here we use the power rule, 2y dy by dx. Minus 4, this derivative is just 2x, equal to derivative of 0 is 9. So see, from here, this is 8x. If I send it over there, I will get 2y dy by dx is equal to 8x. And now divide by 2y. So this is the derivative. See, dy by dx is 4x by y. That is your derivative. So this is called implicit differentiation that we studied in 3.1. Now for the second derivative, and d2y by dx square will be the first derivative of the answer. What is the answer? 4x by y. Now you see, again there are two functions in my, I have to differentiate this, right? Differentiate this one more time with respect to x. So I will need quotient rule. Now this quotient rule was in chapter 2. And that is also coming with us. So y square y as it is, the derivative of 4x, and minus 4x as it is, the derivative of y, which is equal to y into 4 minus 4x into dy by dx. Your dy by dx is given by 4x over y. So I replace the value here. So that's how you can find the second derivative in implicit differentiation. 4y square minus 16x square divided by y cube. So this is my second derivative. Now because the point is also given, if you look at the question, the point is also given. This is xy. So I have to find the curvature at 2, 5. So at the point 2, 5, my derivative dy by dx, which was 4x by y, so x is 2, y is 5, you see, 4x by y, so it is 8 by 5, and the second derivative dy by dx square is equal to 4y square, y is 5, minus 16x square, x is 2, divided by y, which is 5 cube. So you have to simplify this. 100 minus 125. So this becomes 36 by 125. So hence your curvature will be d2y by dx square divided by 1 plus dy by dx whole square power 3 by 2. This is the formula, so I can put everything here. 8 by 5 is 36 by 125 is your second derivative. No need for absolute value because it is positive. So 1 plus dy by dx is 8 by 5 square power 3 by 2. So if you simplify this, you will get the answer. So if I simplify, 1 plus 8 square by 5 square, so this becomes 25 plus 64 over 25 power 3 by 2. So 36 by 125 divided by 64 plus 25, 89 power 3 by 2, and 25 power 3 by 2 is also 125. Why? Because 25 power 3 by 2 is 5 square to the power 3 by 2. So 2 and 2 will cancel, and 5 to the power 3 is 125. That's how I got this. And why I'm writing it? Because 125 will cancel. Your answer will become 36 over 89 to the power 3 by 2. So you can leave your answer up to here. This is fine. If you want to find decimals, you can do that. Use calculator and use the decimals, but up to this answer is fine. Okay, so that is your solution if implicit function is given. Okay, so this 20 is an example of implicit function, because implicit function was given, so we used implicit differentiation. Okay, this is an example of implicit function. That's why I use implicit differentiation from section 3.1. So now you can try other 3 problems that will give you enough practice. All right. So that's it for this lecture. So let me stop the recording first.